Okay, so hi again. Now we're going to talk about some properties of waves. In particular, we're going to talk about reflection, refraction, and diffraction later, but I think I'm going to save diffraction to a separate video. So in this one, we'll focus on reflection and refraction. So just quickly, reflection is an example of here you have an incoming light ray. These green dotted lines are the wave fronts, and the outgoing wave reflects at the same angle here between here and here at which it was incident, or which it arrived. So this angle over here is this angle here, and this is the principle that governs reflection. Refraction is an example of light slowing down when it enters a different medium, or speeding up, just to say changing speed when it enters a different medium. So here we can see the light ray passing through the wave fronts here. You can see the wave fronts around this medium, but inside the medium themselves, they travel a little more slowly. Now this is notice the wavelength has decreased. However, the frequency is going to remain the same. And that has to be if it slows down. You can see that from the wave equation. So V is less, V equals frequency times wavelength, and if V is less and wavelength is less, then F must remain the same. So another example of refraction down here. Here we have a light ray in red, and it enters a more optically dense medium and it bends. And diffraction, just quickly as an example here, light or waves bending around corners or edges of objects. Okay, so between two mediums, you need to be able to sketch incident and reflected or refracted waves. And just to look at that, we're going to look at a one-dimensional example, and that is pulses of waves on a string. So I'm going to come over here to this applet right here. I believe you can see this. And so here we come down. Here's a pulse, just to show you just a simple pulse. And here's what it looks like when you have a reflection from a boundary. So you have a wave, and it meets a rigid boundary. The wave is going to reflect, but it reflects back inverted to whatever it was incoming. So if it came in underneath, it would reflect back on top, or vice versa. Here we can see from a soft boundary, or this here is free to wiggle. This end is like a loop of, or a ring on a pole. It's free to move up and down. You can see the wave is not reflected. This would be an example. We'll see an example below. Here, a reflection from an impedance discontinuity. That's a fancy way of saying, well, if light goes from one medium to another. And you can get both, reflection and refraction. So here we have an incident wave come in, and some of that energy is transmitted into this. In this case, it's a thicker rope, and you can see that the wave pulse is not inverted. But because this incoming wave is meeting something that's more optically dense, we'll have to say, is it's being partially reflected back. And you can see when it's reflected back, it's inverted because it's meeting can we say, a harder boundary, more optically dense. This is an example of this would be just like when we sent the light ray into our refraction cup. Some of the light was transmitted into the water and bent, changed speed. Some of it was reflected from the surface of the refraction cup. And let's see if I can get this to. There we go. Please continue. There we go. And here's an example of from just the opposite from above here. Can I show them both? Yeah. So you can see from a more dense medium to a less dense. So this would be like from water to air sort of thing. Notice the pulse is not reflected here. Excuse me, not inverted, as it's transmitted into a lower optically dense medium. Okay, let's come back here. And here's a diagram that shows both conditions. We have an incoming or incident ray of light, and part of the light is refracted, that's bent inside the medium, in this case water, from air. And part of it is also reflected back at the boundary level. And here's our perpendicular normal line. Here's an example of light coming into a Again, with the glass, you can see it's bent at the boundary, and another normal to calculate the exiting angle, and it's going to be the same angle entering as it is as leaving. In the case where the incident light is directly along the normal line, we won't have any refraction that we could see and detect, but the light does slow down still. So it slows down here and bends toward the normal, speeds up as it bends away from the normal, and here it's slowed down to no bending. So here's a demonstration we did in the sink the other day. Actually, this is a little bit different, but it's essentially it's similar. It uses the same property of refraction. And here's a good applet. Let's see if I can find. Is it this one? Yes, here it is. So this guy's been doing applets. Got a lot of them out there on the internet. They're really, really cool. So here we can actually click and drag, and you can change and experiment, find the angle of refraction and reflection, and based on different the medium. So it actually changes water. Water to water doesn't do anything. But water back to air, we can see, oh, there we go, we can change this and see, hey, there's a place here where, here's the refracted ray, there's a place here, there's an angle at which the refracted ray disappears. Right there, it becomes refracted essentially along perfect, parallel to this boundary line here. And we can say that all the light in this case is reflected. This is what's called internal reflection, total internal reflection. So coming back here, there's an angle at which that happens. That's called the critical angle, and it depends. It's different for depending on what the two medium are. From air to water, it's got a different one. From air to glass, and from air to corn syrup. So here's an example. We see this one's going to be refracted, this light ray. Here's another one that's refracted. Again, a little more refraction as we keep bending, changing this input angle here, incident angle. And here we have another light ray. It's an even steeper angle, and it just barely gets refracted. And then here's an example of the light ray. It's completely reflected internally. So we can say that this over here is pretty close to the critical angle. And we can show that with our refraction cup. Here's an example of light being totally reflected. Applications of this, but this is another graphic. You can see here the critical angle in red, where the light beam is parallel to the surface here, or perpendicular to the normal. Here's some more graphics. You can see it here. TX is a symbol for transmission, so this amount of transmitted light. An example of an application for total internal reflection is fiber optics. You can see a light beam comes in here, it bounces off this surface, bounces off that one, bounces here, down here, and essentially it travels along the fiber. And as long as the fiber doesn't make too sharp of a bend, it should travel along there forever. And it doesn't, of course, go forever, but it goes for quite a long time. And the benefit of that is you can get a lot of information very fast without much loss, as opposed to like copper wire would have, which has a certain resistance per foot or per yard or per mile. So here's your glass core, and you have something surrounding it that's called a cladding. And there's a difference in the index of refraction between the two, so that you can create some kind of internal reflection. So here's a graphic about light bouncing down a channel. And so here's a little quiz for you. You can place these words here. Here's your word bank, and these need to go into the appropriate blank space. So you can try and pick a word and put it in the right spot. So you can pause your video here and watch and put in the answers yourselves, and in a second I'll give you the answers. So pause your video right now. Okay, welcome back. Yeah, so here come the answers. For the first one, it's second one, third, and there you go. There are all your answers. And I see other uses. Here's other practical uses of total internal reflection. So these endoscopes are used to peek in various cavities, whether they be inside the body or inside an airplane. They use these to check for defects and cracks and wear and tear on airplane structures. that you can't see with just the naked eye. And they can also use to check your put one down your throat and check for ulcers and such. Binoculars and periscopes also use reflecting prisms that, based on the principle of total internal reflection, so light comes in here, bounces internally reflected into this one, totally internally reflected into the person's eye. Same with binoculars; they have actually some of these prisms in binoculars also. There's the light path that might follow to your eye. Okay, and we're going to get into Huygens principle in a separate video, so I'll end this one here. Okay, see you next time.